So the idea of today's lesson is, you know what? What if you had a problem that asked you about finding an exponent that's unknown and it didn't turn out to be an integer? So for example, if I said, what's 3 to what power gives me 9? The answer is just 2, right? 3 squared is 9. Or 3 to what power gives me 27? The answer is 3. Pretty easy, 27. But what about all those numbers in between? Ever think about that? Like 3 to 25, 3 to what power gives me 25? I can figure that out. Honestly, like how could you mathematically figure it out? You can estimate, right? Well, 3 squared is 9. 3 to the third is 27. So that means that 3 to some power between 2 and 3 is going to give me 25. I don't know what power that is, but it's going to be maybe 2.8, 2.9, 2.7, something, right? Something I'm going to round, obviously. But the question is presented as, how can we figure out that exact value? That's where I find the power of logarithms. And then they're applied to other topics and applications, such as like earthquakes and any sort of math that goes on powers of 10. Any math, any data that works on powers of 10 use logarithms. So we'll see the applications of it afterward. But I want you guys to recognize where it comes from. Okay, so that's what this first slide is saying here. And this is a different example, but the same concept. Like 3 to what exponent is equal to 8, right? 3 to what exponent is equal to 8. So you have to recognize that it's clearly going to be between 1 and 2. And I'm asking you to really just solve this equation. Right? That's the equation you're being asked to solve. 3 to the x is equal to 8. And in your mind, you should think, oh, 3 to the 1 is 3. 3 to the 2 is 9. So 8 is somewhere in between here, right? Somewhere between 3 and 9. So the x answer must be between 1 and 2. It must be between 1 and 2. Now, with that said, if you didn't want to ever use logarithms, believe it or not, you can still solve this on a calculator. You can graph it. Remember, to solve an equation on a calculator, you graph one side in y1, graph the other side in y2, and then you find the intersection. So no matter what function I give you, no matter what function you are given on a standardized test, if you have a calculator, you can solve that equation. You can solve any equation with a calculator. Any, literally any, assuming there is a solution, a real solution. So if I had, 3 to the x plus 7 equals 8x squared plus 2x minus 4 all over 3x minus 7. Like, I'm not going to solve that by hand and sit here all day. I would graph this in y1, I would graph this in y2 and find the intersection. Let's do that. Let's pull up those calculators real quick. Let's graph 3 to the x in y1, and let's graph 8 in y2. Actually, you want downstairs? I'll take that. So in y1, you've got 3 to the x. That's exponential growth from last class. We know that, right? Because b is greater than 1 in that case. So this is a graph of exponential growth. And y equals 8 is just a horizontal line. So when I'm graphing this, I've got exponential growth. I've got a horizontal line, and they will intersect at this coordinate. What does it become? What is it?
1.892789.
Yeah, so it's 1.89 comma 8. Is that 89 you said, right? 1.89?
Yeah.
So 1.89 comma 8 is my intersection there. Well, the 8 makes sense. It's got to be the y value of 8, right? We're trying to figure out when is this function, which is in red, when is this function equal to 8? So we know the y value is going to be 8, right? That makes sense logically. But look at our x value. That answer also makes sense. Because look over here. 3 to the 1 is 3. 3 to the 2 is 9. Well, then it's got to be between 1 and 2 as an answer. We already said that. And it turns out to be 1.89. If you don't believe that, go to your home screen and type in 3 to the 1.89, and you'll get probably close to 8. It's going to be a rounding, obviously, we rounded this. So type in 3 to the 1.89 on your home screen, you should get around 8. There's something around 8 based on our rounding that we just did. So we could solve this equation today and for the rest of math without logarithms. But if you have to do it by hand, you have to know logarithms. You cannot do this without logarithms by hand. So you have to use a calculator every time, and you're not going to be using a calculator in all of math. Now, to be completely honest, later in life, you will absolutely use a calculator if you're going to be studying like anything with math or engineering or science related. But throughout the next 4, 5, 6 years of your high school and college careers, you're going to have to do this by hand. So we introduced this concept called logarithms. So let's go to see that. So the easiest way for us to define a logarithm today, we'll see a different definition of it tomorrow with a graphical representation. But the easiest way to see it is to use this conditional statement. In this conditional statement, if a to the c is equal to b, then we can say, and by the way, the guy that introduced this was Bernoulli, actually. Bernoulli was one of the guys, another engineer. We can say that if a to the c is equal to b, then the log base a of b equals c. Let's write that down in words underneath here, please. Underneath here, let's write down the log, like write the word the log base a of b, the log base a of b equals c. The log base a of b equals c. Now, the word log is an operator, just like the square root symbol. You guys learned about the square root symbol because you needed to solve equations that said x squared equals 7. And then you just took the square root. But the square root was something that was brand new to you when you learned it the first time, right? Well, logs are going to be brand new today. Don't make it any more difficult than it is, though. It's just like a symbol, like square root. Now, square root is very easy because you can figure out what the square root is because you know it means, okay, what number times itself gives me this number. Log is a little bit different. So we're going to use logarithm properties and some of our other pieces to help us with this process. But I want you to recognize that the word log is an operation, just like the square root is an operation. Just like later in geometry, you're going to learn about sine and cosine and tangent, and those are operations. Okay, that's all they really are. They're functions or operators. So this is our general rule. Now let me point something out. The way I've taught some students in the past to remember this, or memorize it, is that the base remains the base. So the log function has a base of a in this case. Well, the exponential portion of it had a base of a as well. So the base remains the base. Whatever the base of your exponent equation was in exponential form here, whatever this base is, becomes the base of the log. And then all you do is switch the sides. Take the c and the b, take a look where I'm pointing here, and just switch the two. The b that was on the right becomes on the left. The c that was on the left now goes on the right. Good morning.
Where did you find the intersection? How did you find the intersection?
Can you see both graphs?
Yeah.
You press second, and then look on the top for the word calc. On the very top, the top row of buttons, look for the word calc. It's like second. And then look for intersect on there, it should say. And then try to hone in on the intersection. Hit enter when it says graph 1, graph 2, right? Or curve 1, curve 2, it'll say. Just tab over till you get to the intersection. Keep hitting enter. You get around 1.89, comma 8. So again, we're going to keep the base. We're going to make a equal to a, and then we switch the other two. So let's discuss what I'm saying here. So for example, let's use the simplest thing we can think of. Let's say like 2 to the third equals 8. Let's turn this into logarithm form. Well, in logarithm form, the base remains the base. So what's the base in this case? This is great that it rhymes. Go ahead. 2. 2 is the base, I agree. So it's log with a base of 2. And then what does the argument? Argument is b, by the way. Argument is whatever the log is doing. It's taking the log of something. what does the argument over here become if I follow my rule? If I follow my rule, what does it become? Valentina, what do you got?
8 equals 3.
Yeah, so log base 2 of 8 equals 3. That's the form of this exact same statement in logarithmic form. Log base 2 of 8 equals 3. Now, you're just to take it on my advice for now. You can put this in your calculator and do log base 2 of 8 equals 3, and I'll show you how to do that. But for now, I'd rather you just understand it, and then we'll get into the calculator for a portion of it in a little bit. Okay, so again, the base remains the base. Whatever was on the left is now on the right. Whatever was on the right is now on the left. You see what I'm saying there? Base remains the base, switch the other two. Whenever you want to convert in either direction. Whether you're going from logs to exponential or exponential to logs, it's the same concept.
Is the 8 an exponent or is it like a regular?
So the 8 is like f of x. Imagine the log of x. 8 takes the place of x in that sense. That's why I'm calling it an argument. The phrase is argument, yeah. So you are doing the log base 2 of 8. You could do the log base 2 of 10, the log base 2 of 12, and those will all be different values. But we're looking at the log base 2 of the number 8. It's not a multiplication symbol. Write yourself a note that there's no multiplication going on here whatsoever. This is not multiplication. Again, the word log is like a square root. It's an operator. When I ask you to do the square root of 25, you just say, oh, it's 5, because you know that. But the square root symbol is doing something to the number 25 to make it 5. Same thing here. Log base 2 is doing something to the number 8 to make it 3. And we'll see about how this works as we do more and more of these. So I think it would help us to take a look at a couple of just rewriting, and it really would make it a little easier. So let's start with part A. Write each equation in exponential form. So let's go from log to exponential. And if we're forgetting our rule is remember to keep the bases the same, and then switch the other two. So if I want to make this into exponential form, I make the base of my exponent 3. So the base remains the base. The base of 3 becomes the base of the exponent. Then I have an exponent here and a number over here. The exponent and the number, they're just going to be the reverse of these two, aren't they? Flip them around. So what goes in the exponent in this case? Helen?
4.
And what goes as an answer?
81.
Yeah, and tell me, please, isn't that correct? 3 to the 4th is indeed 81. So again, we're just practicing. I need you to understand that. You might not understand necessarily, like, what is this log thing still? Take it on faith that we're just practicing transforming it, and it will clear itself up as we go through. So 3 to the 4th is indeed 81, which makes this statement up here also true. And the way I read it is this way. Ready? 3 to the 4th is 81. Please look up. Ready? 3 to the 4th is 81. That's how I transform from log to exponential. I always make this the base, and then I raise it to the power on the other side, which is the 4, and it equals the argument of the log function always. Let's circle the number 81, circle the number 0.125, circle the number 1/16, and write the word argument. Okay, I'm going to use that phrase a lot. So the argument of the log function is whatever the log is being taken of. And you're going to hear that phrase again with trigonometry, with sine and cosine. If I do the sine of 30 degrees, the argument is 30 degrees. Okay, part B. And part B doesn't look as obvious because I got a decimal, so it makes it a little tricky. But again, the base remains the base. Isabella, what's the base in this case?
2.
2. 2 to what power, Isabella?
The negative 3rd.
Good. I'm going to take the negative 3 and move it over to the left. Then I'm going to take this guy and move it over to the right. Equals?
1.25.
Is that correct? Is that actually right? You want to help me out with that, Isabella? Can you tell me?
Should be 2 to the 1 over 1/3 equals 0.125.
No, I mean, you're on the right track, but I'm asking, how can we prove that this is actually true? Is 2 to the negative 3 0.125? Is that right? What is 2 to the negative 3rd? You were kind of on the right track, but you made a small mistake there.
8, negative 8.
Careful. You're on the right track, but you're thinking 2 to the 3rd.
Yeah.
1/8.
1/8.
1/8. Remember, it's 1 over. So this is really 1 over 2 to the third. Okay? And 2 to the third, as you said, is 8. So if I keep reducing this a little bit further, I get 1/8. And what is 1/8 as a decimal? 0.125. 1/4 as a decimal is 0.25. So we're just showing that these log statements at the top can be transformed into exponential form. And then I'm just proving that this is indeed correct so that I can make this statement as an equality. If this were not the case and these were not equal, then this equal sign is not valid up here. Again, the equal sign in the log equation would not be valid if this weren't true. Okay, in either form, we have an equation. Yes?
Every time you do this, you have to check to make sure it's
No, we're just right now practicing turning into logs, turning logs into exponentials, and then we're going to do the opposite on the next slide. Okay, so the third example, I'm going to keep the base, so the 4 remains 4. The exponent is now -2, and the answer is the argument. Okay? So we're keeping the base the same. The base drops down, and then the number that was over here moves over to the left, which is here. The argument, which was here, moves to the right, which is over here. And what does 4 to the -2 mean? Clearly, it's 1 over 4 to the 2. We just did it, so I'm not going to really ask. And that equals 1/16, and that is indeed true. Okay, these are all true statements. So all we did just now was practice writing from logs to exponential. Second example, same thing. Practice now, though, from exponential to logs. So I start by writing the word log for all of these. The base remains the base, so I can do that for all of them if I want right now. Okay, take a look at what I just did, because I can see all the bases already, so I can start with all of these. I'm a third of the way done with all 3 parts. The base remains the base, and then what do we do after that, Seb? Once the base remains the base, what's the next step?
You put it, switch it to
Yeah, so, yeah, these switch sides now, right? So it becomes log base 6 of,
log base 6 of 1 equals 0.
very good. The second one, again, the base remains the base and switch them. So the second one is log base 8. Again, switch these two when you're talking about the log form now. Log base 8 of, okay?
1/4 equals -2/3.
Eduardo, the last one, log base 5 of
5 root 5
is equal to?
equal to 5 to the 3 hash power.
Okay, and again, I'm not going to prove these ones with log these right now, just yet. Okay, there's a reason I'm not proving those ones. We're not going to evaluate these numbers. But these are all true statements. Again, if you evaluated this in a calculator, you would get -2/3. If you evaluate this in a calculator, you will get 5 to the 3/2. These are true statements. Okay, but all I'm doing right now is having you practice transform from log to exponent, exponent to log. That's all I wanted numbers 1 and 2 to do. We'll get into more of evaluation in a little bit. Any questions on how to do this? Again, it's a skill. A skill always gets better and easier when you practice. Okay? Thank you. Who is that? Right answer right there. I don't know who that is. Only gets better when you practice, right? When you practice. So let's take a look at the next piece after this. So we've practiced enough of transforming. Let's take a look at some of these. And what I'm going to do is I'm going to talk about these properties and why they make sense. But from this point forward, these properties you kind of have to know. But once you understand why they make sense, it becomes kind of obvious, almost second nature. So let's look at the first one. One at a time only. Can somebody explain why the first one makes sense? Can someone explain why the first one makes sense here? Why does that first one make sense? Log base b of a equals log base b of c, if and only if a is equal to c. Yeah.
Well, it's sort of just like common sense stuff about it.
Yeah, it's common sense. Remember we did equating coefficients? When you had x squared on one side and x squared on the other, and one of your coefficients was 7 and the other one was a, well, a must equal 7. If 7x squared equals ax squared, there's no other way. It's got to be 7. So just look at this. This is by inspection, right? Remember, by inspection, you can see that a has to equal c. Has to. That's the most obvious of the rules, okay? Now, rule number 2 actually makes a lot of sense also. How do you prove number 2 right? Well, at first it's like, well, what's this whole deal? Log base b of b to the a simplifies to just a. How does that work, right? It's as if log base b of b kind of cancels out. Like this almost drops off when you get a equals a. You see that, what I'm doing right here? Well, why is this true? To prove that it's true, turn it back into exponential form. To prove that it's true. The base remains the base. The answer becomes the exponent, and then the argument goes to the right-hand side. And look what I get. Again, turn that into exponential form. If you can't see what I'm pointing to, take a look up, or what I'm saying, take a look up. Ready? To turn this to exponential form, we go from b, remember how we do it, b to the a equals the argument. So b to the a happens to equal b to the a. That is absolutely true, which makes this statement also true. So we're proving log truths by just using the exponential expression of that. So by turning this into exponential, we can see that that is true. So whenever this is the case, write yourself a note. Whenever you have the base that's the same as this base here, it's really the equivalent of just a 1. And that's this rule here, number 4. Numbers 2 and 4 are very similar to each other. Okay? Again, log base b of b to the a, it just becomes a. The exponent is all that remains. This is like a 1 here. I know it's not multiplication, so I don't want you to think that way, but it's similar to what we were seeing down here. To see rule number 3 be proven true, just convert from exponential to logs. Convert from exponential to logs. So the base, I'll point to it, the base of the exponent remains the base of the log. So let's write log base b over here. So again, whatever the base was here becomes the base here. And then I take whatever this whole thing is and switch it with this whole thing. So let's take this whole thing, log base b of a, this whole exponent, and move it over, and take this a and move it over here now. So the a goes there, and then we take the whole exponent and move it to the right. And look, we get again a truth, a statement of truth, that log base b of a equals log base b of a. So it's very, very useful to recognize rules 2 and 3 when you're solving equations later on. We're not going to use as much of rules 2 and 3 today, but we're going to see when we solve equations with logs, they can really come in handy. Right? So again, if you take a base and raise it to the log of the same base, the argument is the answer. You see what I'm saying? If that's not clear, you've got to physically look up when I'm doing this stuff, guys. Some of you are just staring at your paper like that when I'm trying to explain it. Okay, here, again, this concept is, well, the base to this power equals this. Well, what's b to the 1 equal to? What's b to the 1? Any number to the 1 is? Itself. So b to the 1 is indeed b. So this is absolutely true again. I can write this in exponential form like I did here, and this becomes like I did here. This becomes b to the 1 equals b. So the log of base b of argument b is just 1. Very useful later on. And again, very useful as a property. If you have trouble with memorization, you got to make flashcards. You really have to do it. There's absolutely zero excuse for not being able to memorize what's going to be probably like 5 to 10 properties, of which they're embedded in each other anyway. Like this property, number 2 and number 4 are really the same thing. Okay, numbers 2 and 4 are kind of the same thing. Again, this concept of a carrying over, this concept of log base b of b being 1 equals 1. Let's see. Rule number 5. Can somebody explain rule number 5, please? Oops. Rule number 5. Go ahead, Isabella.
Okay, so if you put it into exponential form, it becomes b to the 0, and that's equal to 1 because it went to the power of 0.
Yes, exactly right. Any base to the power of 0 is equal to 1. We know that from math. It doesn't matter what the base is. Anything to the 0 is 1. So if we take this and put it back into log form, that's where this log equation comes from. That's where this log property comes from. So what we're showing on the right over here again is simply where the rule comes from. That's all we're showing on the right. I didn't show it for this one, but again, it was b to the first equals b, and that is also true. How about number 6? How about number 6? What's going on there? Yeah, go ahead.
It's asking b to the power of what equals 0, and nothing can equal 0 when you put it to the power, so it's like no solution.
Yeah, there's no solution to this. Very good. That's the question. Very good, Valentina. She just simply took the thing and said, b to what power? They believe we don't know what this is right now, right? We're trying to figure out what this equals. Let's say b, call this x. In your mind, call this x. b to the x equals 0. So b to what power equals 0? Is that possible? Only if b is equal to what? Could this be true? No. If b is equal to
0.
0. But b is never 0. It's one of our restrictions. Because, right, 0 to the 0 is 0. 0 to the 1 is 0. 0 to the 2 is 0. 0 to any power is still 0. So the only way that this statement is true is if b is 0, which has no significance on the problem, because in the exponent it doesn't even matter. Because 0 to any power, right? 0 to any power is 0. So this is not going to be anything that makes sense or logical. So let's write that down, that you can never take the log of 0. Rule 6 is pretty much telling us that you can never take the log of 0. It doesn't matter what the base is. Log base 2 of 0, log base 7 of 0, log base 20 of 0. No matter what it is, you cannot take that log. And the last rule is called change of base. Change of base. And what this allows us to do is it allows us, and this is a little bit weird, it allows us to take something that has a log with a given base and a given argument and rewrite it with what's called the common log. Let's talk about this for a second. So remember how the square root symbol, what's the index for a square root symbol really? What's the index for a square root symbol really? Mara? 2. The index for a cube root? Okay, right? But do we show the 2 on the square root? The common log is the same thing as a log with a base of 10. But when you see the word log by itself with no base, assume the base is 10. It is absolutely acceptable to write the word log without a base. And when it is written that way, it simply means the base is 10. Your calculator has a button on it that says log. It assumes the base is 10. So if I wanted to find the log base 2 of 5, I can't do it on the calculator unless I use this change of base formula. So again, log written like this is really log with a base of 10. And I should really put log of x. Sorry, let me make this a little bit more clear. The log of x is really the same thing as writing log base 10 of x. It's called the common logarithm. The common logarithm. It's another one called the natural logarithm, which we may have time to get to before the end of the year. We shall see. Okay, but this is really important because now, if I go to my calculator, right, I'm going to pause for a second. I'm going to pause and go back a slide. Very good. On the right track. Keep going. Keep going. What's 1/9 as a base of 3? Remember, we always want to have the same base. We did this last section. What's 1/9 as a base of 3? 3 to what power?
-2.
Good. So this is really 3 to the -2 to the x equals 3 to the 1/4. And when we get to this stage, if you remember from last class, we did this already. We did this last class. This becomes 3 to the -2x equals 3 to the 1/4. And then we just set -2x equal to 1/4 and solve for x. Becomes -1/8. If you go ahead and check in your calculator and literally type this in right here using change of base, you will get -1.125. Okay, -0.125. You're looking at it like it's wrong. Is there a mistake? You're just confused for a second.
Well, if we do -2x equals 1, we divide it by -2.
Mm-hmm. So I'm putting the -2 down on the bottom, really?
Yeah, so 1 would be 2.
So that makes that an 8 by putting a 2 down on the bottom. 1.5 of a quarter is an 8.
Yeah.
There's a quarter here and that's having it. So listen carefully. There's one more slide to go. Part C you can finish. In the last slide, take a look. In the last slide, I'm going to give you hints because I want you to finish this tonight. Ready? Here's what you want to write down. If it's in logs and you're having trouble solving, make it exponential. So that's parts A and B. Convert parts A and B to exponential to solve. Again, convert parts A and B to exponential to solve. For parts C and D, what do you think you're going to do? You're going to go from exponential to logarithms. And this -1 should be in the exponent. It does not matter, but I meant for that to be in the exponent there. So just correct that, please, okay? But again, convert these to logs to help you, and then use your calculator to figure out these answers. But here you can convert these to exponential. Are your homeworks on the next slide? Please practice this stuff.
Thank you.
Please practice this. Have a good day, guys. Don't forget, tomorrow is your quiz. 10-1 and 10-2.
Is office hours tomorrow?
Tomorrow's Wednesday. Up, office hours in the morning. Absolutely. Have a good one, guys.
Thank you.
You're welcome. Have a good day, guys.